calculate this gradient for each individual weight in our complex network. This is where the genius of backpropagation comes in. It uses a fundamental calculus concept called the chain rule. Think of it as assigning blame. If the final prediction for R3 is wrong, which weights are most responsible? The weights connecting to the output layer? Or the ones further back in the hidden layers? Backpropagation starts at the output layer and works backward. First, it calculates how much each weight directly connected to the output layer contributed to the error. This is relatively straightforward, as these weights directly influence the final output. For each output node, we calculate its local gradient, how sensitive its output is to changes in its input, considering its activation function. This tells us how much a small change here would affect the final error. Now for the clever part, propagating this blame backward. The error signal from the output layer isn't just used to update the last layer's weights. It's also passed back through those weights to the previous hidden layer. This is the chain rule in action. The error at a hidden node is a combination of the errors it contributed to all the subsequent nodes it connects to. We essentially multiply the error signal coming from the next layer by the weight of the connection it traveled through. Once we have this propagated error for a hidden node, we can then calculate the gradient for the weights connecting to that hidden node from the layer before it. The full gradient for any weight is essentially the error signal coming back, multiplied by the local gradient of the node it connects to, multiplied by the input that fed into that weight. Once we've calculated the gradient for every single weight and bias in the network, we can finally update them. The update rule is simple: new weight equals old weight, learning rate times gradient. The learning rate is a crucial hyperparameter. It controls how big of a step we take down the error landscape. A small learning rate means slow, cautious steps. A large learning rate means bigger, potentially unstable jumps. This entire process, forward pass, calculate error, backward pass, backpropagation, update weights, constitutes one training iteration. We repeat this thousands, even millions, of times, showing the network many examples of handwritten digits. With each iteration, the weights and biases are subtly adjusted, and the network gets better and better at recognizing R3. Let's put it all together. We start with our handwritten 3 as input.